Sine and cosine aren't the only trig functions on the planet, so we should probably look at some integrals, some tricky integrals involving other trig functions. We're going to concentrate on tangent and secant, mostly because in typical situations, those tend to be the two that come up more frequently. It just turns out, for reasons that we will see later, that cotangent and cosecant don't actually show up that much. So we'll concentrate on tangent and secant. So to start with, I guess we'd better know what is the integral of tangent and what is the integral of secant. For tangent, leaving this as it is isn't helpful because we don't know the integral of tangent. So we need to do something here. And something that might occur to you is we could write tangent in terms of sine and cosine, like this, sine over cosine. And seeing this, you might think, oh, this looks like a u substitution situation. So let's try, right, often if you have some weird fraction you're trying to integrate, the denominator is something you might choose for u. So let's try u equals cosine x. That means du is negative sine x. Right, and we can move this minus sign to the other side. So this becomes integral of 1 over u, right? This cosine is just u, and sine of x dx together make minus du. Now we can integrate. We get negative natural log u, absolute value really, plus a constant, of course. And then we need to undo our u substitution. So negative natural log, absolute value of cosine. And then as a finishing flourish, some people like to take this minus sign, right? One thing you can do with minus signs if you have them in front of a log is move them to the exponent inside. So we get natural log of 1 over cosine x, but that's secant x. You don't have to do it that way. You could leave it as this form above with cosine and a minus sign in front, but some people like to not have the minus sign there, I guess. So. All right, so there's the integral of tangent. We just had to do a little u substitution. Now for secant, finding an antiderivative for secant is actually trickier, and I don't really have a good intuitive explanation for why you would do what I'm about to do. So I think this is just one of those cases where back in the days when people were figuring out calculus for the first time, they ran into this sort of thing and just tried a bunch of stuff. And lots of it didn't work, but this thing worked. And so now to figure out the integral of secant, everybody does this. So the trick is, this is a trick that's really just for finding the integral of secant or cosecant. The trick is multiply secant x by a fraction. Now this fraction is going to have to be equal to 1, so whatever shows up in the numerator and denominator, it has to be the same thing in the numerator and denominator. And the magic combination is secant x plus tangent x, which I don't know why that is something that you would try, but it turns out it works. So let's see what this gives us. We can multiply through in the numerator, so we get secant squared x plus secant x tangent x divided by secant x plus tangent x. Now this may still look like an incomprehensible mess, but if you look just at this piece, secant squared, that's the derivative of tangent. And this piece, secant x times tangent x, that's the derivative of secant. So this whole thing is actually set up to do a u substitution. We can let u equal secant x plus tangent x. Then du is derivative of secant x is secant x times tangent x plus derivative of tangent x is secant squared x. And when we do this u substitution, the denominator is just u. Everything in the numerator, together with dx, all makes du. And so the remaining numerator is just 1. And now we can, right now integrating is straightforward. We get natural log absolute value u plus a constant, and then undo the substitution, natural log of secant x plus tangent x. So it's no wonder we couldn't guess an antiderivative for secant. The antiderivative for secant is kind of crazy. Okay, so armed with these ingredients, we can actually dive into some more complicated integrals involving tangent and secant. Okay, let's have a look at this one. So secant cubed, tangent cubed. Since we have an odd number of secants, we aren't going to be able to turn some secants into tangents and be left over with secant squared. So we can't use this idea for a u substitution, that the derivative of tangent is secant squared. So that one isn't going to work. But remember, one other possibility to think about is that the derivative of secant is secant x times tangent x. So if we can set aside a secant and a tangent for a u substitution and only have secants left, then we're all set. So let's see, if we set aside one factor of secant and one factor of tangent, what does that leave us with? It leaves us with a secant squared and a tangent squared. So can we turn everything here into tangents, or into secants? Yes, because we have tangent squared. According to the Pythagorean identity for tangents and secants, tangent squared is, let's see, what is it? It's secant squared x minus 1. So times secant x tangent x dx. And now we're set up to use this u substitution. So now we can take secant x for u, and then du is secant x tangent x dx. So the u substitution gives us the integral of u squared times u squared minus 1 du. And then multiply this out, integral of u to the 4th minus u squared du. And do the antiderivative, 1 over 5 u to the 5th minus 1 over 3 u to the 3rd plus a constant, and then undo our substitution, get back to our secants. So 1/5 secant, 1/5 secant to the 5th x minus 1/3 secant cubed x plus a constant. All right, and there we go. So if you can set aside some secants and tangents and have either secant squared left over with everything else tangents, or secant tangent left over with everything else secants, then you can do one of these u substitutions.